Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. We're on AP Physics, this Unit 3, Work, Power, and Energy. Thought we'd give one problem here where we tie in energy to centripetal motion. So teachers introduce centripetal motion at different times in this course. Sometimes they've introduced it with centripetal with the force, the dynamics unit. Sometimes they don't do it until the gravitational unit. So if you have been introduced to centripetal motion, then this problem is fair game in Unit 3. If you have not been introduced to centripetal motion yet, then you won't see this problem until probably the second semester. All right, but I want to go ahead and put this in for those who have seen centripetal motion, and however your teacher introduces it is the right way to do it. All right, we're going to start with, we have a little roller coaster, a little car here, so I'm going to draw my little car. All right, it's a toy car. And it's coming down this roller coaster track and it's going to make this loop. We call this the loop-to-loop problem. All right, they like to call this loop. The loop-to-loop problem is kind of its little nickname, or loop-the-loop problem, something like that. So anyway, but that's kind of what this problem's called. So what they're going to be asking for is two things first, and then I'll show you how they can ask for something else. But they're going to want this minimum velocity here, V-min, when this car, now remember this car is making the loop, so it's going to be kind of upside down in here. When it comes down and then it's upside down, just like a great roller coaster, which I do love, a great roller coaster and a good loop, as long as the physics has been calculated correctly, of course. And then they want that minimum velocity there at the top of the loop, and they also want what this minimum height is. What's the lowest you can start this car that it completes the loop and it doesn't just fall down and crash. All right, so we're just going to get started. First of all, the first thing to recognize is we have a change in height here. We went from an initial height to we're going to be at a different height here. We're going to be at rest at the start, and it's going to be moving here, obviously, because we have a velocity. When I see a change in height, I know I'm already thinking in my head, oh, conservation of energy. So our mechanical energy before has to equal our mechanical energy after, or final. All right, and maybe I'll put initial instead of before to keep it consistent. And they're also going to tell you that this is a frictionless track. All right, so we're not going to have to worry about friction here, which means that all of your potential energy and kinetic energy at the beginning will equal all of your potential and kinetic energy final. All right, now the other thing I'm going to see is that my cart is making a circle. It's not rotating on an axis, it's actually moving in a circle. So I'm also going to think, hey, centripetal force is probably going to play into this. All right, so that's a lot of times I get from students, how do I know where to start these problems? We're getting more and more problems, more and more equations in our equation tool belt, we like to call it. Let the problem guide you. I see a change in height. I'm going to look at change in the conservation of mechanical energy, and then also in kinetic energy versus all potential here, kinetic and potential here, because I've got height plus it's moving. All right, and then I'm seeing it move in a circle, so I'm going to go to Newton's second law for centripetal motion as well. All right, so I'm going to go right here. I'm going to start here because they asked for this minimum velocity. And so far my equation doesn't have velocity in it. I'm going to do a free body diagram. That's how we always start problems with forces. So I'm going to do a free body diagram on this position. I'm going to call number 1 right there. All right, if I did an FBD on that, and I'll just come over here and do an FBD. This is my cart. The track is kind of above it. Right, so we have force due to gravity down, we know, and we're going to have a normal force down. All right, so that's that is the two forces that we have on that cart down. Now when I say down, it's really center seeking when I say down here. So here's the center, and both of these forces are center seeking, meaning they're both going to be positive, because remember, center seeking is positive. If it's in the opposite direction and it's facing away from the center, then it's negative. That's how we define our centripetal forces. So these are both going to be positive because they're both center seeking. All right, Perfect. And they're both centripetal forces because they're center seeking. So I'm just going to write that in. I've got N positive plus a force due to gravity equals mass. And I'm going to remember that my centripetal acceleration is v squared over r. All right, so I'm putting v squared, that velocity squared, divided by the radius of this loop. And that was capital R, so I'm going to stay consistent here and use that a capital R. Now, here's the deal. We had to get velocity in here if we want minimum velocity. Okay, now here's the concept in this problem. If you have minimum velocity, it means at this top, the wheels have just barely come off the track. In other words, they're not touching the track anymore, but it's still got enough momentum that it's going to continue to make that circle. All right, so it's not so slow the wheels have come off and it's just crashed down, but the wheels have just barely lifted off the track, but the momentum's going to keep it moving in a circle. Well, if that's the case, then normal is equal to 0 because the wheels are not touching the track any longer. All right, so you have to have a surface pushing if you have normal. And you're like, but wait a minute, did you even explain why normal is down? Well, because look, this is the surface. The surface always pushes perpendicular to the object, right? So this surface, the car is not on top. If the car had been on top of the track, then normal would have been up. But since the cart was underneath the track here and is upside down, then normal is down as well as force due to gravity always is, or center seeking, we should say, instead of down. All right, so that cart was on the inside of that track. That's why it is center seeking and down. All right, but if the wheels have just come off, it's not touching. That means there's no normal because there's no surface pushing on it at all. So normal equals 0 at minimum velocity because the wheels have just barely come off the track. Or lost contact, we should say, with the track. But they're going to pick up. The wheels are going to pick up right here, and you're going to go around the loop, and everything's going to be fine. So here we go. So that's 0. So now force due to gravity equals mv squared over r. And remember, this is minimum velocity. Force due to gravity is mg. We know that. And look, everybody brought mass to the party, Q party in the USA. Well, I'm going to multiply R over. I have RG equals V squared. That's a V, not an R. And I'm going to take the square root. So my minimum velocity is going to be related to the radius of that circle times my constant of G, 9.81. All right, and that's going to be my minimum velocity. Now they asked for minimum initial height. Okay, we said, hey, there's some change in height here. On this side, we only have potential energy due to gravity because that object is rest, so no movement, so no velocity, which means no kinetic energy. All right, and then when we get to this point though, so I'm doing this from the start. So let me tell you where I'm doing this from the start to that position 1 of the loop. Position 1 in the loop. Okay? Now, when I get to position 1 in the loop, I have potential energy again, gravitational, because there's a height here, and that's going to be its final at that position, plus, not final totally, it's going to come back around, but final for this position, and then we are moving, so there's kinetic energy as well. All right, I'm going to call this mgh naught. I'm going to call this height, now look, if this is r, that's 2r, so the height of this, the whole height is just the diameter, 2r. All right, so it's going to be mg. I'm going to go ahead and put h final, and then I'll plug that in for you so you can see that. All right, look, everybody brought mass to the party again. Yay, Q party in the USA. So I have g times that h naught, which is going to be the minimum, because I'm going to use minimum velocity here, equals g, that h final, and I'll write it over here so we don't forget it, that h final for this loop here is just 2r. All right, that's 2r plus 1/2 v squared, and that's going to be that minimum velocity. Okay, now I just need to get h initial by itself, because that's what I'm trying to solve for, that initial height that's the minimum. All right, so I'm going to take h naught equals Let me just go ahead and do another substitution in here, because look at this. My V minimum is R, the square root of R times G, our constant. If it's squared, then V squared is, and that was a V, that does not look much like a V, but it is RG. So I'm just going to sub in RG for this V squared. So I'm subbing it in right there. Okay? Now look, everybody brought G to the party. G, G, and G. 9.81, little g, everybody brought to the party. Q, party in the USA again. And your H naught is 2R plus 1/2 R. If you were to add that up, that's 5/2 times the radius. So your initial height, if you want minimum initial height, it is dependent on the radius of that loop. And if you want the minimum velocity, where normal is 0 because the wheels have just barely come off the track, then it's also going to be related to R and to your constant G, 9.81. That's how you do this problem to find minimum velocity and minimum initial height. Now here's what minimum, that was hard to say. Now the other thing that they might ask you is they might give you, like this would be given, and it would be greater than minimum. If it's greater than minimum, you do this whole problem. They would give you height, and they would give you radius of the circle, and you go all the way through this to find your velocity, and it won't be minimum, because if this is not minimum height, your velocity will not be minimum. All right, so you would start, instead of how we started on Centripetal, this was our part A, and this was our part B. If they give you a height, and they give you a radius would be given, and they want you to find your normal force, is how they could reword this problem, then you would start now with mechanical energy. You would find a value for your velocity. All right, and then you would plug that value in to your centripetal motion. You would know R. Your mass is going to cancel out. Well, actually, it's not. They're going to give you a mass at that point too. You're going to find your normal. It won't be 0 anymore. So right here, you would end up having normal equals mv squared over r minus force due to gravity, which is just mg. I'll go ahead and erase that and show you that that would be mg. All right, so you would go through conservation mechanical energy to find this velocity, plug the velocity in here. They would have given you mass and radius, and you could have found a normal force. Now that would all be if it's not minimum height and not minimum velocity, and that car is actually on the track and the track is pushing it. And so you would just do the problem backwards. Those are the main ways they would ask for this problem. I hope that helps. Thank you for watching. If you liked this video, please give it a thumbs up. If you want to listen to more of our videos, we have Unit 4 coming at you in the next couple of weeks. Please subscribe, and thank you for watching, and happy physicsing.